Hey guys, sorry I had to be out again today. My son was sick on Friday and my daughter got sick tonight. But today we were going to go over the two problems I left for you on Friday. So we're going to go ahead and do that by this screencast. And then I have another problem for you guys to try today. Post it on Google Classroom, and I will be back one way or the other tomorrow. If one of my kids is still sick, my wife will be home, so I will be here. So for this problem, guys, it's similar to the demonstration that we did in class on Friday. And third period, sixth period has made a video that they've put on Google Classroom. So if you scroll down, you will see it. So you can watch this as well, similar to the first problem. So for this problem, we have a disc that has a ribbon wrapped around it, and we're going to release it, and then what will happen is it will fall down and unravel as it falls. So for part A, we have been asked to draw a free body diagram showing all the forces acting on the disc as it falls. So of course, since we have the ribbon attached to the left hand side, we should see an upward force on the left, and that force will be tension. And then from the center of mass, we should have the weight going straight down. So you should have a free body diagram that looks just like this for part A. Alright, and then we'll move on to part B on the second page. So for part B, it asks us to figure out the acceleration of the disc as it falls. So I've redrawn our free body diagram here, and so what's going to happen is, first of all, the force down minus the force up is the net force, so that should equal the mass times the acceleration. Alright, so mg minus t equals ma. And then also, because the tension is acting away from the center of mass, we will have a torque from the tension, and that is our net torque, which has to equal I alpha. So once we sub in for I and alpha, we get TR equals 1/2 mr squared times A over R. All the R's cancel out, so we'll see that T equals 1/2 MA. And then to finish solving the problem, I'm going to take the 1/2 MA and I'm going to sub it in for T in the other equation. So as you can see, we have M in every term, so the M's cancel out. So we get G minus 1/2 A equals A. So G equals 3/2 A. Therefore, A has to equal 2/3 G. So for this problem, we should see that the disk accelerates downwards with a value of 2/3 the acceleration due to gravity. Part C asks about the direction of the motion as it falls. If you look at the free body diagram, you can see that the tension is straight up and the weight is straight down, and there are no forces to the left or to the right. Therefore, the acceleration has to be straight down. So those are your answers to parts A and B and C for the first free response problem I left you guys on Friday. Alright guys, so for the second problem, we have a Atwood machine with a 1 kilogram mass on the left, a 2 kilogram mass on the right, and we do see that we have a heavy pulley. The mass of the pulley wheel is 3 kilograms, and they tell us the moment of inertia of that pulley wheel is 1/2 times the mass of the pulley wheel times r squared. Sorry, make that 1.5 times the mass of the pulley wheel times r squared, which is really not a possible value, but we're going to go ahead and work it with that anyway. That's a mistake that was made when this problem was modified, but we're just going to work it with that value of 1.5 times m times r squared. We'll also notice that the base of the system itself has a mass of 5 kilograms, which will become important later. So for part A, it asks us to draw and label all the forces acting on M1 and M2, so I'm going to go ahead and do that on the diagram above. So for mass 1, we should have its weight going down, M1G, and we should have a tension, T1, going up, and T1 has to be bigger than M1G. Then on mass 2, we should have a T2 going up, And then we're going to have M2G going down, and M2G should be bigger than T2 because M2 is going to accelerate down and M1 is going to accelerate up. Also on the pulley, guys, those same tensions will act, so T1 is going to be down on the left-hand side, and T2 is going to be down on the right-hand side. And once again, T2 has to be bigger than T1 to give the heavy pulley its clockwise angular acceleration. And then finally, on the pulley wheel itself, we will have some normal force from the axle. And we will also have the weight of the pulley wheel. We will also have some forces acting on the base, which we'll talk about later on. So for part B, it asks us to use the symbols from our free body diagrams to come up with equations for the translational motion for each of the two blocks and the rotational motion of the pulley wheel, and we'll do that on the next page. Okay, so for part B, we're going to first write the equation for the hanging mass M1. And for that mass, it's going to accelerate up, so I have the force up, T1, minus the force down, M1G, equals M1A. Then I'm going to write the equation for mass 2. And since that one's accelerating down, I'm going to have the force down, M2G, minus the force up, T2, equals M2A. And I'm going to go ahead and solve both of those for their tensions. And then finally, we're going to need the rotational motion equation for our heavy pulley wheel, so I'm going to write that out as well. So for the pulley wheel, we have our clockwise torque minus our counterclockwise torque equals the moment of inertia times alpha, and I've subbed in for everything there. And so now what I'm going to do to finish this equation is I'm going to go ahead and take my value for T1 here and plug it in for this T1, and my value for T2 there, and plug it in for that T2. And I can also go ahead and cancel out all of my R's. So now I get the equation M2G minus M2A minus M1G minus M1A equals 1.5 MA. I'm going to get all my A's together on the right hand side, factor out the A, and divide to get my final equation. So I end up with the equation M2G minus M1G over M1 plus M2 plus 1.5 big M equals A. So now I can plug in my values and solve. So I get 2 times 10 plus 1 times 10, nope, that should be minus. Alright, 2 times 10 minus 1 times 10 over 1 plus 2 plus 1.5 times 3, and that will come out to 1.33 meters per second squared. Then for part D, it asks us for the tension for the mass M1, so that's just T1. We already figured out earlier that equals M1G plus M1A, so we just plug that back in and solve. So once we go in and do that, T1 equals M1G plus M1A, and it comes out to 11.33 newtons. And then finally we have to do part E, and we'll do that on the next page. So here I have a lovely drawing of the pulley wheel and the stand, and the reason I've drawn that is the pulley wheel and the stand together are both in translational equilibrium. The pulley spins, but it's still in translational equilibrium because it doesn't accelerate up or down. So if I think about the forces acting on the pulley wheel and stand, there are really 4 important forces. One of them is T1 on the left hand side of the wheel. One of them is T2 on the right hand side of the wheel. Another one is going to be mg, and that's the mg of the entire thing, both the pulley wheel and the stand together, which is going to come out to 80 newtons. And then finally, I've got the normal force coming up from the bottom of the stand supporting the entire thing. That's the normal force coming up from the table. So for that, the forces up have to equal the forces down. So the normal force from the table has to equal T1 plus T2 plus mg, and remember that's mg for the whole 8 kilograms, the 3 kilogram wheel and the 5 kilogram stand. We solved for T1 on the previous page. We also had an equation for T2, so we're going to go ahead and solve for that now. So when we do that, T2 is going to equal M2G minus M2A, which comes out to 17.33 newtons. So the normal force from the table has to equal the 11.33 newtons for T1 plus the 17.33 newtons for T2 plus another 80 newtons for the 8 kilograms total for the stand and the wheel. So the normal force from the table will then have to equal 108.67 newtons. And I hope that problem makes sense to you guys now. I've got one more modified Atwood problem for you guys to try today, and it is posted on Google Classroom. So go ahead and give that one a try for the rest of the period, and I will see you guys tomorrow.